Thank you, Alberto. Thank you so much. Good afternoon to everybody. Thank you for the presentation by Alberto. As Alberto told you, I am a geologist, and actually I am a hydrogeologist. So a geologist devoted to the study and research about groundwater, the water located below the ground. And in these 3 hours, 3 hours with 3 breaks between them, I will try to give you some take-home messages about the importance of groundwater and generally the water in relationship to the possible drawbacks coming out from the climate change and the effect that this climate change could determine on our society and on our system. I have put in the first slide my email address for any further contact you would like to have with myself in the following future. And I start with the first 2 slides in order to present more or less the matter, the topic of my lecture. Well, I will talk about hydro-geology, so the relationship between water and the subsoil and what is happening, what is acting below the ground. And basically the relationship between water and geology, water and soil, is on two main topics: groundwater, that is the translation in English of the Italian term falda, that is the water that I call down under. You know that Australia is down under respect to Italy, respect to many thanks. Oh, because the administrator told me that the screen was shared. By the way, we are verifying this, and I think that I'm not able actually to put in exchange. Okay, I try again. I try again now, and let's confirm to myself if now oh, thank you so much. Okay, now I go to presentation. The screen is always shared. It's okay. Are you looking at my slide number 2 now? Okay, perfect. Sorry for that. Okay, yeah. So water down under. So the water that, like Australia, are located at the opposite part respect to our world. So groundwater is located below the ground. So actually in a place where we don't have direct experience of what is happening, and we don't have a clear idea of what is groundwater and how is groundwater located below the ground. That's the first main object of my lecture, to give you the idea of how groundwater is distributed below the ground. But the relationship between the water and geology is not also below the ground, but it is also above the ground. And you can see this video. I have also put in share in the Virtuale platform this video in a PowerPoint presentation called videos. So you can see this video when you want in the future. And we are in Taiwan Island during August 31st, 2013. And you see here an incredible rock fall of earth and blocks, very huge blocks of rocks coming from the slope in a very rainy season, in a very rainy period, giving you the impression of the relationship between rainfall and the dynamic of the geological slope of the slopes of the valley and the impact against human beings and the values of human beings, and also giving you the idea of the unpredictability of this event in terms of location and possibility of damages, and so the importance of preventing them by a proper knowledge of the processes and a proper planning of the activity of man subjected to this risk. This is a very good example in this video of what we call hydrogeological risk, a risk due to the water involving soil and rocks on the surface, obviously. Well, for that reason, my presentation will be subdivided basically in 5 topics. Hydrogeology, topic 1, water cycle, climate global change, adaptation, resilience, and mitigation. And during the presentation, during the different slides, you will see in color one of these 5 sectors in the bar below in the slide, putting in evidence the different part of the lecture. In the first one, we are talking about where the water is below the ground, where is located, and which are the relationship between the water in the ground and the dynamic of the Earth's crust. You see here on the right, the famous Vajont landslide that occurred in northern Italy a lot of years ago in 1963. In the topic 2, we will see the relationship between the water in the soil and in the ground and the water cycle, putting in emphasis, emphasizing the fact that groundwater, soil water are not a separated body, but are strictly related to the rainfall, to the atmosphere, and to the water cycle. For example, you can see here the relationship between a river and groundwater, or the importance of the water in inducing, for example, a debris flow that is a very destructive landslide. Continuing in the climate global change, we will see how the climate change, that basically is a phenomenon related to the atmospheric dynamics, but also the global change, so the variation in soil land use and of different economical practices in the world can affect groundwater and can affect the soil in relationship, for example, to intensive over-exploitation of water resources. And on the other hand, or as a consequence of climate change. So, for example, the warming of the atmosphere and the modification of the regime of the rainfall. The final 2 topics will be related to adaptation and mitigation. Adaptation, in order to show you how is resilient to climate change is groundwater, and how groundwater could be a way, in some way, to react to the negative effect of climate change. And finally, mitigation. So active procedure, active tools in order to mitigate the effects of climate change. Well, let's start from the first topic, the importance of groundwater. This is very important because you know very well that the planet, our planet, is a planet of water, basically, But for the 97%, the water in the planet is located in the sea, is sea water, so is salty water. But to reflect upon this, the remainder 3% respected to this 97% is fresh water, so not salty. But be careful, of this remainder, about 3/4 of the remainder, 77% of these 3% is ice. So is basically located in polar sheets, glaciers, and icebergs. And only 1/4 of this 1/3 is liquid fresh water. But be careful again, of this 1/4, a very, very poor percentage, this 1% of this remainder, is the surface water that we see every day, of surface water on which we have direct experience, the water in the lakes, the water in the rivers, the water in the atmosphere and in the soil moisture. But this water is a very small portion of the liquid water in the earth. So basically, the most huge reservoir of fresh liquid water in the earth is below the ground. It's not Garda Lake, it's not Po River, it's not the big lakes or rivers that we see from which we have direct experience, but is a reservoir located below the ground. This is a very important take-home message to be considered. Other important thing, you see here in this slide, for example, that we have this proportion between the volume of surface water on a global scale and the water and the volume of groundwater on the global scale. You see 4.2 millions of cubic kilometers of groundwater respect to about a bit more than 1/10 of 1 mega cubic kilometer in the case of surface water. There is a ratio of 1 liter of surface water volume for 33 liters of groundwater. Groundwater intended in the first 750 meters below ground surface. So it's a very huge reservoir of liquid water occurring below the ground. But where this big reservoir is located, perhaps many of you have the imagination that the water in the ground is hosted in caves, in big spaces, in subterranean rivers. Nothing so magic and so fascinating, but basically the water is contained into the ground, into the soil, into the rocks, because the soil and the rocks are porous. They are not made up by a material that is continuous, but is a porous material. And inside these pores, groundwater is hosted and is located. Many of you, perhaps, when they are thinking about the spaces below the ground where water can be hosted and can flow, they imagine these pictures: caves, stalagmites, stalactites, subterranean lakes, very magic world. Not at all. Yes, obviously, we have also these caves, we have these karst environments, but for the most part, the water in the ground is contained in this way. These, they seem like potatoes, but they're not potatoes, they are sand grain, obviously enlarged at a certain size. You have to imagine that each of these small rock fragments is about 1 millimeters, 2 millimeters of size. And between these sand grains, you have pores, you have voids. And inside these voids is located water, is located groundwater. And you see this as an image of electronic microscope. You see the sand grains and you see the primary interstitial porosity between these sand grains. And the groundwater is contained in these pores. But how much porous is a porous material? Let's make a guess about a distribution of spheres of equal size. Also big spheres like this one, or smaller spheres like this one. Imagine to fill one room of all of these spheres with the same size from the bottom of the room to the ceiling, and to pour the water inside this room and to calculate how much volume of water is needed to fill all this porosity. How much, in your opinion, is the maximum porosity of this room, intended as the fraction between the volume of the pores and the complete volume of the room? How much could be this fraction with this distribution of spheres, in your opinion? Have you some idea? You can answer directly by the microphone if you want. Well, I see, I listen no question. The ratio is about 48%. So imagine on a total volume of a room, a bit lower than the half of this volume is void. And in this void, water can be contained. And so groundwater can be contained. Obviously, these spheres could be assembled in a different pattern. For example, in a more compacted way like this one. In this situation, the porosity is lower, is about 26%. So more or less is the half of the preceding value, but it's a rather high value. So there is a lot of pores in the ground. And inside these pores, you can have groundwater hosted and free flowing in the pores. And this is another important aspect. We have also to talk not only about the possibility of the soil to host the water, but also to make the water flow. The first concept is the concept of porosity. The second concept is the concept of permeability. Permeability is, you can see here in the slide, the aptitude of a porous material to transmit water, and is related to the size, the shape, and the connection of voids. If a material is a good conductor of water, it's called an aquifer. Aquifer is derived from the ancient Latin, is a carrier of water, is a porous medium capable of carrying the water. And if we make a well, make a drilling in an aquifer, we can exploit the groundwater located in the aquifer because the groundwater in that aquifer is moving in a good way. Let's see these examples of natural rock. This is a pumice. Pomice in Italian is a rock produced by volcanic eruptions. It's very porous. You see, it's like a groviera. It's very full of holes. But these holes, like bubbles, are not connected between each other. And so this pumice is not permeable. It's porous, but not permeable. On the other hand, we can present another type of rock, is a clay. Argilla in Italian. Clay is a rock that can be molded, can be modeled, is very plastic. And the clay is made up by microscopic particles lower than 2 microns of diameter and microscopic pores. And in the clay, you can contain a lot of water, But this water is not moving because these pores are so small that the capacity of the water to move is practically not permitted. And so we are talking about a not permeable, an impervious material. The idea is a sand, like in a beach, because the sand has rather high pores connected between each other, and so is porous and permeable. And the sand, when it is located below the ground, is a good aquifer, capable to transmit water, capable to transmit groundwater. Obviously, a sand could be cemented during the formation of rock, and you have the cement that are filling the pores. And if there is a cementation, the rock cannot more be capable to host groundwater. But you see here the obliteration, the filling up of the pores by the cementing, and so there is no more water that could be hosted in the pores. But a rock could be fractured, could be subjected to fracturing. And this fracture, like this one, could be capable to represent pathways to the flow of groundwater. So groundwater could be hosted or in the interstitial porosity of sediments, for example, in a sand, or in the fracture in a rock. And obviously this capacity, the permeability in the fracture rock is strongly affected by the opening of the fractures, by the frequency of the fractures, and by the interconnection of the fractures. So if we have very fractured rocks, these rocks could represent a good aquifer to be exploited by wells, by exploitation of groundwater. Well, let's go. You see here at the bottom of the slide, the hydrogeology part of the bar is not in blue, but now is in red. When it is in blue, we are talking about groundwater. When it is in red, we are talking about the relationship, the connection between the water and the soil, inducing a landslide. What is a landslide? A landslide is a movement of a mass of rock, earth, or debris down a slope. You see here a very destructive landslide body over a highway in Taiwan in 2020. Also, this type of phenomenon is related to water and is related to water and geology. And we are talking in this way about hydrogeological risk. But in this way, the effect of water in respect to geology is different respect to the groundwater, because the process is on the surface, is more fast in terms of velocity, and it implies the modification of the geotechnical parameters of the soil, inducing a landslide. What is the main motivation? What is the main cause of a landslide? You have a landslide along a slope when the destabilizing forces are higher than the resistant forces. If the resistant forces that are on the numerator of this ratio are higher, you have a situation of safety, a situation of stability, whereas the destabilizing forces are higher and the denominator, the safety factor is lower than 1, and you have a landslide. And what is the main motivation to inducing this destabilization? Is the water. Because the water inside the soil reduces what geotechnicians call the shear strength of the material, la resistenza al taglio in Italian, And this shear strength is responsible to maintain stable a slope. If you have a plenty of water, this shear strength is to be lowered, and so the destabilizing forces are higher than the resistant forces, and you have a landslide. And you can have a landslide like this one on the slide. So the water could be an opportunity to determine a resource in the ground like groundwater, and at the same time a factor of hydrogeological risk if there is a plenty of water at the surface, determining an increase of destabilizing forces. Many of the problems due to landslide and soil collapse are due to water. You see here a famous happening in Florence. We are here near Old Bridge, Ponte Vecchio, in the left bank of the Arno River. Arno River is here, and perhaps you recall a big collapse of the levee of the bank of the Arno River some years ago. And this collapse is another phenomenon that in some way is related to the water and to the water contained in the material of this levee, of this bank, of this argine in Italian, located on the left bank of the Arno. And landslide and soil collapse are studied by engineering geology. And the engineering geology basically is a branch of applied geology that study the relationship between the water and the soil capable of inducing landslides and soil collapse. Whereas hydrogeology is related to the groundwater flowing into the ground. And the problem in terms of not correct management of groundwater are related to groundwater over-exploitation and groundwater contamination. Well, we are seeing the first topic of our lecture. Now we start in the second topic, water cycle. What is the relationship between the water cycle and the hydrogeology water, so the water below the ground or the water at the soil surface? Obviously, it's evident with this connection, but it's very important in our consideration about the effect of climate change. Because if climate change induces modification on the rainfall regime and on atmospheric temperature, these modifications are reflected in the water cycle, and the water cycles induce effect on groundwater and on landslide. For example, concerning groundwater, you see a scheme of a possible conceptual model of groundwater flow system below the ground. This is the surface of the landscape. You see a river here, and you see some pathways of arrows depicting some trajectories below the ground. And you see some time frame near the trajectories, days, years, centuries, millennia. You see also an area called recharge area and another area called discharge area. This is very important in groundwater flow system because below the ground, the water flows very slowly, much more slowly than surface water, from a recharge area, an area from which the water infiltrates from the surface into the ground. There is a more or less long pathway in the ground with a more or less long time span of the water flowing into the ground. And finally, the water drops out, comes out in the discharge area, for example, a river here. So it's very important, the conceptual difference between the movement of groundwater and the movement of surface water. Surface water, for example, in a river, flows very easily, very fast, very in a very direct, experienced way by you. You see a river flowing with a, for example, a velocity of 1 meter per second is normal for the flow of a river. On the other hand, below the ground, you have a huge volume of water. You recall the huge volume of groundwater flowing very slowly along time scale, much more longer respect to surface water. This concept is very important in terms you will see in the next part of the lecture in relationship to the resilience of groundwater to climate change. Basically, you have the recharge from one side, a flow in the ground, a discharge from another side. If there is a continuous equilibrium between recharge and discharge, you are in a steady state conditions. Like economic steady state budget, you have a certain amount of money entering in your wallet, and you have the same amount of money coming out from your wallet. If you are in a stable state, in a steady state, there is an equilibrium, and the level of water table, the level of piezometric heat, the level of the water below the ground become stable. There is no variation. But if, for example, you have a decrease of recharge, for example, for climate change, lower precipitation, increase of temperature, increase of evapotranspiration, you have a decrease of recharge, and so you have also a decrease of discharge on the other part. For example, spring discharge is lowered, and there is less water for the exploitation of groundwater. So it's important, the connection between the groundwater flow system and the recharge. The recharge is the main aspect by which the climate change could affect groundwater flow system. You see here I imagine, rather simple scheme of groundwater flow system below the ground. You have a stream, you have a rainfall, you have infiltration through vertical movement. You have a groundwater flow system in the aquifer and the discharge into the river. You have a spring here, you have a continuous process. But if there is a modification, for example, in the precipitation regime, you have also an effect on the groundwater flow system and an effect to the stream itself. So this is to give you the idea of the connection between the water cycle and what is happening below the ground. Two nice pictures of springs. What are springs? Springs are the process, a spring, sorgente in Italian, is a process by which the groundwater is discharging out of the soil, out of the rock. And you see above here the conceptual scheme of a spring: precipitation, infiltration, flow of groundwater below the ground, entering out from the soil of the groundwater, forming a spring. So the discharge of the spring, this is a very beautiful karst spring in the Alps. This is another two examples of spring in the Montebaldo area near Verona, to the east of Garda Lake. If you have a decrease of the precipitation, a decrease of recharge, a modification of recharge, you have a modification also of the discharge of the spring. But the groundwater flow below the ground is even more complex than this and could be represented also by a tube, a pipe under pressure. You see here an area of recharge of an aquifer. The water is entering here. The groundwater is flowing inside this, for example, sandy body. And above and below, you have two layers, two strata of clay. So very impermeable strata. Well, if you make a drilling, a well, perforating the top of this sand and of this aquifer material, the water is coming out to the surface by an artesian process, forming an artesian well. And this is an example of how the water could arrive to the surface also by artesian pressure process, due in the last instance to what? To the recharge from the surface. If this recharge is going to be changed by climate change, you have also an effect on the groundwater flow system and on the pressure of this aquifer. Not only rainfall is important, but also temperature. You know well that perhaps one of the most sure effects of what we call climate change is the increase of air temperature in the last years, in the last century. If you have an increase of temperature, we have also an increase of evapotranspiration. So of the water that is going from the liquid state to the gas state, to the vapor state. But if we increase the evapotranspiration, we have a decrease of liquid water capable to infiltrate and going to recharge the aquifer with a process that we name effective infiltration. And for that reason, also a modification of temperature has an effect of recharge and on groundwater flow due to the increase of evapotranspiration. The process of recharge is so important, and recharge is so complex, is a complex process. You see that the recharge could have different origin. Recharge in Italian could be translated as ricarica. Is the process by which the aquifer is replenished, is supplied by rainfall. And the recharge could be direct from the infiltration of the water, indirect from the rivers, focused in local high infiltrability locations, but also incidental by the anthropic activity, irrigation, sewer system, leaking pipes. Which are the drivers of recharge? The effective rainfall, so the precipitation minus evapotranspiration. The snow is very important, the snow in the recharge process in terms of intensity of snow and permanence of the snow cover to the ground, the soil water content, and the land use. And which are the factors of recharge? Climate, obviously, because climate has an effect on effective rainfall by the temperature and the precipitation and on the snow. At the same time, geology and geomorphology, but also global change. With global change, we mean not only climatic processes, but also anthropic derived processes due to modification of land use, for example, irrigation, modification of regime of rivers, and so on. Here you see, for example, an example of focused recharge in karst. Karst is very particular rocks, very porous. You see the presence of vertical conduits, horizontal conduits, and the formation of important springs. And the recharge of an important karst system is related to the precipitation. Well, I think we could perhaps have some break. I think it's good to make some interval between my dissertation of geology, hydrogeology, and a possible relax of you that are listening to me. So I propose to you to make a break. I have a bit lower than 15 minutes. So around a 4:45, we are going to begin the second of the third of the three part of this lesson. If you don't have any questions, I recommend a 12 minutes break. Okay? Thank you. Okay, I am here again. I saw that there are some questions in the chat. I'm sorry to having missed the question before, and I try to reply to the question of Maria Livia. Could you repeat how it's called the equilibrium between recharge and discharge of water? Yes, I go to the slide of the reference, is this one. This equilibrium is called steady state. And when you have the equilibrium between the quantity of water entering into the ground by the infiltration process with the quantity of water exiting out from the ground by the discharge process, this equilibrium is called steady state. It is a situation of equilibrium between input and output. That's the way of how in hydrological sciences, in hydrogeology, we define this equilibrium. And about the question by Marco, underground water can flow upward due to negative pressure gradient. That's right. I'm going to show you the reference slide about this. Yeah, because you have to consider this stratum, this layer of sand, like a pipe. And this pipe is recharged by water at the top in the recharge area. And the level of the water here determines the level of recharge that is in a higher elevation position. Then the water is flowing inside the sand in pressure condition. And this dashed red line is a virtual surface called the piezometric surface that determines the distribution of the pressure inside the aquifer. So if I drill a well and making basically a hole in the top of this aquifer, by pressure from a position of higher pressure here, the water is rising up, and for the principle of the communicating voids, communicating vases, obviously this water has the tendency to arrive to the same level of the piezometric surface. It's impossible to do this because otherwise the wells could have a very high elevation above the ground. But the motivation is that we have a higher pressure here, a lower pressure here, and so the water is flowing due to this gradient of pressure from higher pressure zone to lower pressure one. A picture of this situation I have shown you, I'm sorry, in one of the first slides here. This is a picture of an artesian small wells, artesian piezometer, and you see the water coming out by pressure from the ground. I hope to have replied to the questions, and so I would like to continue the lesson from the slide where I have stopped before. Sorry, I'm going to the, sorry, one moment. I'm sorry, I have interrupted the, now I put in exchange the presentation. I'm sorry, yes, now the presentation is okay. And I would like to arrive to the slide of before. Sorry for that. Okay. And this is the slide. Are you seeing the slide with Emilia-Romagna like here? It's okay? Okay, Serena, can you confirm me that I exchanged the desktop? It's okay? Okay, perfect. Well, I would like to give you an idea of the distribution of the aquifers, so of the rocks capable to host the groundwater inside them and to let the groundwater flow in a permeable way in the mountainous portion of Emilia-Romagna region. These different colors are related to geology, and the geology is described in the legend of the map. There are some strange names, perhaps only geologists could understand the meaning of these names. Turbidites, for example, is sandy deposits deposited in the very far past, geological past in oceanic floor. And all these lithologies are capable to produce groundwater. And you can see here on the right in the red some idea of the coefficient of effective infiltration in percentage. What is the coefficient of effective infiltration? Is the proportion expressed in percentage, in this case, between the water that infiltrates into the ground and recharge the aquifer and the total amount of effective rainfall. What is effective rainfall? Effective rainfall is total rainfall, so total precipitation coming from the sky, from the clouds and from the process of precipitation, minus evapotranspiration, minus the water that is going back to the atmosphere by evaporation and transpiration. So you have a certain quantity of rainfall, you eliminate evapotranspiration, the resulting quantity is capable in part to infiltrate and in part to flow over the ground. Well, the percentage of infiltration is this one. And you see that for the most part, in the majority of Apennines, we have a percentage of infiltration between 20 and 40%. Is not so high because it's not so high the permeability of these rocks. Respect, for example, to karstic system or other types of rock, much more permeable than the rocks forming the Northern Apennines. By the way, notwithstanding with these, it's a good proportion of water, and the aquifers of Emilia-Romagna region in the mountains are the most valuable groundwater resource occurring in this region. Well, you see at the bottom, we have changed the color. Now we are talking not of groundwater in relationship to the water cycle, but we are talking of landslide process in relation to the water cycle. And this is a very important aspect. Water in the soil could be a factor of cohesion to put together the grains. You see here sand grains, and this in blue color is a very thin film of water, capillary water. And these are clay particles, and this is a very thin film of water. And this water in this quantity is capable to let the porous material to be stable, to be cohesive, to be not moving, not fluid. So until a certain degree, the water in the soil is a factor of safety, is a factor of cohesion. But over a certain threshold, over a certain limit of water content, the soil is going to be more and more liquid. And so, for example, if it is dry, the material behaves like a solid. If it is moist with capillary water, the material behaves like a plastic solid, but still stable. But if it is wet with a lot of water, and if it is very wet, the material becomes fluid and more fluid. And obviously, in that way, the materials is going to be unstable. And this instability is obviously a factor of risk and a factor of also catastrophic outcomes. You see here in this table the speed of landslides. This is interesting because we have talked before of the very slow motion of groundwater that can flow below the ground for millennia, for centuries, with a very slow motion inside very small pores. Whereas in the surface, the effect of the water could be dramatically different. You see here different classes of the speed of landslides, the description from extremely low speed to extremely rapid speed. On the right, you have the speed in meters per second or in millimeter per year, meter per hour, and the effects of these different speed of the process. And going from above to below, from the top to the bottom of the slide, you imagine to have an increase of water content, an increase of fluidity, and so an increase of velocity, and an increase of damages produced by the landslides. And you see in this video, another video that I'm going to show to you. This is a monitoring of a landslide in Northern Apennines. We have some black period because we are during the night, and all the video is accelerated. And you see when there is strong rainfall that the velocity of motion of the landslide is much more rapid due to the increase of water content. The water content is capable to transform a plastic, not very fast moving mass of soil in a very fluid moving mass of soil. And this is an example of the effect of high water content in the movement of the soil. Well, so we have defined what is hydrogeology. We have defined that the water, when we talk about hydrogeology, can be related to the position in the subsoil, like groundwater. We have seen also the relationship between this groundwater and the water cycle, the recharge in particular. And concerning landslides, we have seen how important is the water content in determining the speed of landslides, and obviously how landslides are connected to the water cycle. Let's come to the third topic of our presentation, and so the effects of climate change and global change, both on groundwater and landslides. I'm starting from these maps of Emilia-Romagna region, showing you, giving you an idea of the modification of rainfall regime in our region, in this region. We are through 4 seasons of the year. the fall, the winter, the spring, and the summer. And in each of these maps, you see the difference between the average seasonal effective rainfall. You recall, effective rainfall, total rainfall minus evapotranspiration. And you see the difference between the average value in the 30 years period between 1991 and 2018 with respect to the period between 1961 and 1990. There are two blocks of 30-year periods. Where you have a red, orange, or yellow color, the value in the more recent 30-year period is lower respect to the preceding one. Whereas if you have a blue or more darker color, the value in these 30 years, in the more recent 30 years, is higher. So what do we see? We see that particularly in the mountainous region, we have an increase of precipitation of about 10% in the area of the mountain region during the autumn, during the fall. Whereas in all the other seasons, we have a lowering. Due to the fact that the temperature in fall is not so high with respect to other season, for example, summer, these could determine on a global regional scale a lowering of effective rainfall in the last 30 years. But in the fall, there is an increase of intensity, an increase of effective rainfall. And so we have a complex effect of climate change. It's not always a matter of lowering, but we have to see the seasonal base effect of this distribution. I think that Alberto Montanari has given to you the idea of the variability of the rainfall distribution according to different seasons and how it's complex to define the dynamic of rainfall on a seasonal basis. But be careful. If we call about rainfall, it's not so dramatic, the modification in the more recent 30 years respect to the older ones. But look to these two graphs on the bottom of these slides. This is the snow cover, the thickness of the snowpack falling in the mountains during the winter. You see from 2002 to 2016, a progressive lowering of the thickness in centimeter of the snow cover during time. And on the right, you have the permanence of the snow cover in days to the ground. And also this permanent is dramatically decreasing in the last 15, 20 years. This phenomenon has a dramatic influence of recharge because the permanence of the snow cover on the ground is a factor that is going to favor the recharge, to favor the supply of water to the groundwater. If the snow cover disappears very rapidly due to an increase of temperature, you don't have the time to let infiltrating the water below the ground. And so you have a negative effect to the recharge. And we can estimate the loss of about 13% of direct recharge in the more recent 30 years with respect to the older 30 years before. This is an effect of climate change in the sense that there is a lowering of the thickness of the snow cover and of the permanence of the snow cover to the ground. This picture gives you a plastic idea of what I'm talking about. This is a location in the Western Alps in Piedmont region. You see the winter season with all the snow cover on the mountain. This is a karst massif. And in this position, you have a spring that is discharging from a big fracture in the rock. But you don't see any spring here because we are in the winter. And so most of the water is not infiltrating. But due to the snow melting during the spring, you have obviously the melting of the snow, the slow melting of the snow, the infiltration into the ground, and you have the production of the discharge to the outlet. You see here in a very effective way the connection between the recharge on the surface of the rock and the discharge at the outlet. If this snow cover is going to be decreased, and if this snow cover is going to have not a very permanent period of stay on the surface because the melting rate is very rapid, a lot of the water is going for overland flow on the surface, is not infiltrating, and so you have a lowering of recharge. And if you have a lowering of recharge, you have also a lowering of discharge of the spring. But when we talk about climate change, we have also to talk about global change. There are too many important differences between these two concepts because basically climate change is related to the dynamics of the atmosphere. But global change is determined by the behavior of man, the anthropic activity. And perhaps at the moment, the effects against the groundwater are more severe when originated not by climate change. We have seen before a lowering of recharge of about 10–13%. It's not so much for the moment, but is due to the changes in groundwater use and the increasing of over-exploitation of aquifers. This is actually a real impact on groundwater. What is global change? How global change does act on the process of groundwater flow? You see here different activities that we can list in the term global change actions. For example, clearing natural vegetation and forest with the transition from natural vegetation to arable land, converting pasture to arable land, extending and intensifying irrigated agriculture, importing surface water, reforestation or afforestation with commercial woodland, the activation of precision irrigation, the urbanization. All these activities, also if we consider no acting climate change, are capable to dramatically affect water budget. For example, from one point of view to the increase of recharge, from other point of views to a dramatic decrease of recharge and modification, complete modification of soil water budget, and also affecting salinity, recharge, and pollution. So perhaps at the moment, the effect of global change actions are more severe than climate change actions. And this is very important to be considered because the capacity of man to induce modifications in the water cycle is very important. For example, irrigation. I think that irrigation practices is one of the most important impact on groundwater. And this impact could be affected in different ways. For example, if you use groundwater for irrigate arable land, you are going to overexploit groundwater. But at the same time, if you irrigate an arable land in so a heavy way, you have in a paradox, you have an increase of recharge because much more water is added to the subsoil. At the same time, if you use groundwater to irrigate, you can determine a salinization of the soil because the groundwater is too much saline, and the evapotranspiration could induce salinization effect of soil. Whereas if you use surface water to irrigate, the salinization process is not so high. Such different aspects induces many impacts on groundwater, much more impacts respect to climate change itself. The modification of soil end use, it's more capable to induce this impact. What about the overexploitation of the aquifer? Let's consider this data. Let's consider this, how much water is consumed by man. How many liters a human being living in a gatherer-hunter technology, so very pre-industrialized, also pre-agricultural technology. How many liters of water are necessary to sustain a gatherer-hunter human being for drink purposes or domestic purposes? Very few liters, about 2, 3, 4 liters per day for one single human being. How many liters do you put in discharge when you go to the toilet and you use the toilet for your domestic private utility, private purposes? It depends on the intensity of the flush of the toilet, but we are around 12, 15 liters of water for one single flush. How many liters of water are provided to the municipal water supply of Bologna for each inhabitant? I'm talking about the water consumed in your houses for domestic uses, for the washing machine, for the cooking procedures, and for the irrigation of your flowers in the balcony. How much? 250 liters per day per inhabitants. This is more or less the average rate that is provided for a municipal water supply. So from 234 to 1510 to 250. How much water is provided actually on average for a citizens in US, for a citizens of New York? Is about 500 liters per day. So you see a dramatic increase of consumption of water from a very pre-technological situation to the need of a municipal water supply. And this is only for an aqueduct. I'm not talking about irrigation. I'm not talking about industrial uses. This is only for an aqueduct. It's very impressive, the increase of the exploitation of water resources. Nowadays, at global scale, 36% of the water that is exploited, both in the groundwater resources, is subjected to the use for potable water supply. About 2 billion of people in the world rely upon groundwater for drinkable water supply. The majority of water the majority of groundwater is exploited for irrigation. That's the main destination of groundwater exploitation. And about 1/4 is exploited for industrial use. And this exploitation is increasing in time. You see here from 1960 to 2010, the increase of groundwater abstraction in the world, also the increase of global water demand, global change, the increase of the production of food, the necessity to supply food to a ever increasing quantity of people. And at the same time, you see the increase of groundwater depletion of the aquifer. That's an interesting thing, because obviously if you increase the overexploitation, you have also an increase of the depletion. The depletion is the empty of the reservoir. But the rate of the empty of the reservoir, it's not going at the same rate than the groundwater abstraction. So there is in some way, until a certain degree, a resilience of the groundwater system to this overexploitation, because in certain situations, an increase of exploitation determines an increase of recharge. And so you exploit more groundwater, but you recall more water coming from the surface. And so in some way, there is a buffer to this increase of overexploitation. Which are the effects of overexploitation of the aquifer? Many are these effects. For example, the watering. You see here that the aquifer is completely emptied by the action of pumping from deep wells. And so there is the chance that a deep wells could impair the possibility of other smaller depths well to produce groundwater. But you see also on the right, you recall the scheme of before, recharge, discharge. If you pump out too much groundwater from the aquifer, you don't, the only effect, you don't have not only the effect of lowering the piezometric surface, but you have also the effect to lower the discharge to springs, because all the system is connected. Sorry, and if you increase the pumping out, you decrease this discharge, for example, to natural groundwater flow system. And this is another important thing to be considered. Another drawback of the groundwater abstraction is the salinization of coastal aquifer. Along the coast, along the shores, you have the continent, you have the sea. Below the sea floor, the water contained in the porous medium is salty, and below the continent, the water contained in the soil is fresh. And so you have an equilibrium between the fresh groundwater and the salty groundwater. And this equilibrium is represented by this surface that determines an equilibrium between fresh groundwater and salty water. And the water you see is coming from the continent, flowing slowly and discharging to the sea. And this is an equilibrium. This is a steady state condition because there is a continuous supply of water and a stable equilibrium. But if we have a pumping by a well or by many wells, like it's occurring commonly in the coastal area, you have a salinization of the aquifer because you have the decrease the depression of the piezometric surface and the upconing of salty water from below. And so you have a disruption of this equilibrium and the process of salinization of the aquifer. The salinization of the aquifer along the coastal areas is the most important effect of over-exploitation of the aquifer due to global change. In this scheme, you see different ways of groundwater salinization, not only related to the pumping in the coastal areas like this situation. You see here in pink color the salty water and in blue color the fresh groundwater. But you see also that excessive pumping can induce the rising of salty water coming out from the bottom of alluvial basins, or from the production of oil in the reservoir of hydrocarbons, and also from the irrigation practices I was telling you before, that if you use, for example, groundwater for irrigation, particularly in arid and semi-arid climates, you can have salinization of the soil. All these practices induces water salinization and so impair the groundwater quality. But the problem is not only related to salinization, but also to the subsidence. What is the subsidence? The subsidence is the lowering of the soil surfaces due to the lowering of the pressure of the water below the ground. We talk about natural subsidence due to natural geologic phenomena and artificial subsidence due to pumping. The rate of natural subsidence is very low, is between 0.7 and 2 millimeters per year. So the soil surfaces is getting lower during the time with this rate. But if the rate is between 30 and 70 millimeters per year, we are talking about artificial subsidence. And this artificial subsidence is due to pumping, to groundwater pumping. You see here, for example, the plain of Emilia-Romagna between the foothills of Apennines here from Parma to Rimini, and Ferrara, Rovigo until the lagoon of Venice. And this is the rate of subsidence in the period 1942-1999. Very strong subsidence in the Bologna area, very strong subsidence in the delta of the Po River, very strong subsidence in Ravenna. Why? To groundwater pumping, also to methane's reservoirs in the delta area. Very high. And this subsidence is dangerous because it's not always coherent in the same way, but many places of the landscape subside in a higher rate with respect to surrounding ones, and this determines a negative effect on the buildings, on the stability of the buildings. Here you see a profile showing you the distribution of the subsidence rate from Piacenza to Rimini along the Emilia Road, La Via Emilia, and you see the higher subsidence rate is near Bologna. You see here Borgo Panigale and Ponte Samoggia. Here we are near important water wells, exploiting groundwater for municipal water supply. And this strong pumping of water wells determine a strong subsidence of the ground. And this could have an effect, a geotechnical effect against buildings. You see here, for example, a famous slide in the San Joaquin Valley in California from 1925 to 1977. in 1925, that is the location of soil surface. And then you can see the dramatic decrease of the position of the soil surface due to the intensive pumping of groundwater. This is an extreme demonstration of one of the possible negative effects of overpumping in the soil collapse, in the subsidence of the soil. And this is a very famous example, but around the world, we have many other ones, like, for example, in Mexico City, in some coastal area, in Indonesia, and something like that. In this scheme that is derived from some slides of this website of the International Association of Hydrogeologists, I recommend to you that if you are interested in see the effects of climate change and global change on groundwater resources, to browse to this site, because there are many interesting schemes and pictures and movies and videos giving you the idea of this effect. In this picture, you see the ways how the modification of rainfall, snowfall, irrigation, interactions between rivers and groundwater are capable to induce effects of groundwater by climate change and global change. So recall, not only climate, but also the activity of man that in some way are induced by climate, but not only by climate, but also by the anthropic activity and the economic development of man's activity, could have an impact on groundwater. In some way, more severe impact respect to climate change. Well, you see the red color on the bar in the bottom. So now we are talking about the effects of climate change, global change, or landslide. This is a very interesting graph about extreme events. These are data coming from the ARPAE. ARPAE is the regional authority of environmental protection in Emilia-Romagna region, and ARPAE has also a meteorological service, and this meteorological service makes some analysis of the behavior of rainfall intensity. And this is a very interesting graph. You see from 1990 to the left to 2019 to the right, so more or less nowadays period. These are the 365 days during the year. The day number 0 is the 1st of January. The day number 365 is obviously the 31st of December. And these are the 12 months in Italian, sorry. And you see the different extreme event of precipitation with a intensity of rainfall higher than 30 millimeters per hour in the Emilia-Romagna region. And each of these dots is a single event, and higher is the size of the bubble, higher is the intensity of the event. And what we see from this graph, that for the most part, these events are concentrated between June and October, November, because the energy of the atmosphere is capable to determine more intense event in this part of the year. But we observed also an apparent increase of the intensity of this event during the time, and this obviously cannot not have an effect on water resources, because a higher intensity of rainfall, and so a higher concentration of rain in a certain time lapse, in a very short time lapse, induces a higher frequency of landslides, because you have a high concentration of water in a very small portion of an area, or also a flash flood, not only a landslide. On the other hand, if much more water is concentrated in a very short period of time, there is less proportion of water that can infiltrate into the ground, and much more water is running above the surface to the sea. And so there is lower recharge respect to a more regular distribution of this event. And you can see here a typical example of a debris flow. This is a video showing you the effect of the high quantity of water coming into the watershed in the upper part of this watershed, and how this intense meteoric event could induce the formation of what we call a debris flow. What is a debris flow? It's a very fluid mixture of water and material that have an incredible capacity to transport very big blocks of rock with a very destructive behavior. In this case, all the debris flow is concentrated inside the bed of a canal, so without having any effect outside of the banks of the canal. But by the way, this gives you the idea of what a very intense event in a very concentrated short time could have an effect on the transport of sediments, and obviously on the effects of buildings, of man's activity down gradient. Well, now we start the last two items of our dissertation, of our lecture: the resilience and the adaptation to climate change, and the mitigation. Perhaps it's time for another break, another more or less 15 minutes of break. If you have some questions, I'm checking with the chat before I missed this step. Otherwise, if you don't have questions, we can stay here again in, I recommend 10 minutes from now. So at 5:45, we continue the lesson. See you. Okay. I'm here again to go ahead with the last third of our lecture. So I'm going to talk about the last two topics of the lecture, the adaptation resilience topic and the mitigation topic. I go in presentation. And I'm commenting with you this picture that is about the discharge area of an oasis in the desert. This obviously is a provocation, but this actually is a process, is a natural process of groundwater discharge, where we observed in an oasis, the fossil groundwater discharge in arid climate. Why fossil? Because this groundwater is discharging out in a complete arid conditions, and it is the expression of groundwater recharged in different climatic conditions respect to the actual one. For that reason, we call it fossil groundwater, representing a world, representing a situation completely different from nowadays. And why is this a provocation? Because this is an example of how groundwater could be resilient to climate change. In that case, is a natural climate change, not a man-induced climate change. This is a picture showing you the conceptual scheme. You have the oasis, you have a groundwater flow system inside, and for the geological structure of the soil, in this area, you have the discharge of the system. But the recharge nowadays, is practically absent because the system is arid. And in which conditions is it possible to have this situation? Well, we have before to make a comment, because I have explained to you that the rocks and soils capable to host and let flow groundwater are called aquifers, water carriers, permeable formations. But not all the permeable formations are resilient in the same way to climate. You see here these two examples. A very huge groundwater reservoir with a water table with a piezometric level distant from the ground surface. Whereas on the left, a small groundwater reservoir with a water table very near to the surface. This on the left is more sensible to climatic change. This on the right is more resilient to climatic change. And this is due to the fact that the aquifer on the right has a more slow motion, slow flow, and has a very big size, very big extension. And for that reason, you have to reflect, to think about a giant buffer, un tampone in Italian, a giant buffer to the climatic variations on the surface. More huge is the system, more deep is into the ground, more resilient is to the modification of the climate at the surface. It's like a big elephant in the subsoil with a very big memory, very slow in movement. Whereas The aquifer on the left is like a mouse, so it is more rapid, is more reactive to the modification of the climate. Well, I will like to show you an example on a global scale. There are many fossils aquifers in the world, like, for example, the High Plains aquifer in Northern America, the Nubian sandstone aquifer system in Northern Africa, the Kalahari Desert Basin in Southern Africa, or the Great Artesian Basin in Australia. All these are very huge, very deep, and very slow flow aquifer, recharged in a climatic condition different to the actual one. And the extreme example, for example, is the Nubian sandstone aquifer system that is located in Northern Africa, more or less across the borders of Libya, Egypt, Chad, and Sudan. And this big aquifer was replenished during the pluvial period of the Sahara region, when during the last glaciation, the Sahara was a humid climate. And so the recharge was very high. The infiltration of the water was very high. And this gave the chance for this big aquifer, for this very huge sandstone system to be replenished by groundwater. But today, the recharge in this region is practically absent, 5 millimeters per year. You have to reflect that in Bologna, for example, the recharge is about 100, 150 millimeters per year. So the recharge nowadays is practically nil. There is no recharge nowadays. But if you make wells in this aquifer, you obtain a big quantity of groundwater. And this groundwater was recharged thousands of years ago, when the climatic conditions was very different from nowadays. Obviously, this is an extreme example, but this is an example of climate change from a pluvial conditions to arid conditions. And the only water resource on which you can rely for your development is groundwater in that region. It's not surface water, because there is no surface water. There is aridity. This is a good example, extreme example, of how groundwater could in some way react to climate change, also to extreme climate change, to provide the water resources, also if the recharge conditions are completely different from the preceding one. Nowadays, Libyan people exploit very much this aquifer. Obviously, this aquifer will be completely deplenished with this pumping rate, because there is no more the recharge like in the pluvial climate. I'm not saying to you that this is the possibility to overcome the effect of climate change perennially, in a perennial ways, because in this case, you are exploiting in a mining way. We are talking about groundwater mining in this way, but it's a way to reflect that the groundwater resource, the water resources more resilient to climate change are the groundwater resources, because they have a much more slowness of time frame respect to recharge in differently from surface water resources. There are many other advantages to use groundwater resources. Groundwater resources are natural filtered by the porous medium. So groundwater has a higher quality with respect to surface water. Groundwater in many situations is naturally protected from pollution. It is occurring also, like the example before, in arid areas. And it's a huge quantity of liquid water. You have seen at the beginning of this lecture the big volume of water inside the ground. But there are also some drawbacks. Not everywhere you have groundwater. Often groundwater is too much mineralized, and so it's not so good quality for drinkable or irrigation purposes. If you contaminate the groundwater, it's much more difficult to remediate the contamination. Groundwater is much less subjected to remediation process in a technically feasible way and sustainable way with respect to surface water. And you have already seen before the effects of overdrafting, salinization, subsidence, diminishing of environmental flows. But also in Emilia-Romagna, there are many areas in northern Apennines where groundwater are not so highly exploited, but could be a reservoir for providing good quality water supply in period of lacking, in period of droughts, for example, in period of extreme arid condition at the surface. We have seen different drought period in some years, also in Emilia-Romagna in the last time. And from this point of view, groundwater resources in the Apennines could be a way to overcome this drought period. Let's reflect. These two buckets show you the proportion of surface water to groundwater for all global use. And it's interesting to see that the proportion is the same between the global scale and the Emilia-Romagna scale. At the global scale, at the Emilia-Romagna scale, you see that more or less 1/3 of the water for all uses, industrial, irrigation, municipal water supply, comes from groundwater, and 2/3 comes from surface water. Why, if the quantity of liquid groundwater is so much higher with respect to surface water? The answer is because it's more easy to exploit surface water. Surface water is more accessible. It deserves lower skills of technologies to exploit the groundwater from the ground. Not all the rocks are capable to supply, to provide the same quantity of water, but it's we have to reflect upon this because we exploit more surface water, but the bigger quantity of water is below the ground. And concerning Emilia-Romagna region, you see, for example, that public water supply for municipal aqueducts has a higher proportion of groundwater respect to surface water. 61% in Emilia-Romagna is exploited from ground to provide water to the municipal water supply, whereas for irrigation and for industry, the proportion is lower. Why? Because the quality of groundwater is better for respect to surface water. And so for municipal water supply, we use more proportion of groundwater respect to surface water. So there is a chance, perhaps in the future, in a period of the modification due to climate change, also to the effect of global change, to make more development to the use of groundwater. What about the adaptation resilience to landslides? Here the problem is different, because the problem is not to forecast the unpredictable. You recall the giant block of rock near the car in the Taiwan rockfall, and the beginning of this lesson. It's very unpredictable, the phenomenon of a landslide. The problem is not to avoid to have a landslide that more or less are a natural phenomenon, but to avoiding to be involved. So to plan the location of facilities, of buildings, of urbanization in an area that are far from the risk to be involved by landslide. This is an example of the landslide of Las Colinas. Is an earth flow damaging and destroying a part of the urbanization in San Salvador in 2001. How dangerous was to build houses in this area subjected to this landslide? That's the issue. A correct urban planning. On the right, you have the Rigopiano avalanche. You recall in Abruzzo, 2017, a big avalanche. An avalanche is a mass of snow, rock, and other material coming down from the top of the mountain, completely destroying a hotel. But this hotel was located in the proper manner respect to the risk of avalanche. Perhaps it was not located in a proper manner. So in that way, we have also to be resilient to the effect of climate change, also be very careful to the planning of activity, respect to the possibility to have a landslide. And for that reason, we have to evaluate the risk, the hydrogeological risk, the risk of a geological event is related to three features: the hazard, the vulnerability, and the exposure. The hazard is related to the severity of the event and to the probability of outcome of the event. For example, an avalanche, a landslide. The vulnerability is our defense capacity against this threat. And this defense capacity, it depends also on our ability to plan the urbanization of the society, taking into account the geological knowledge of the process and the hazard of the process itself. If we construct in a hotel at the foothill of a possible pathways of some avalanche, also if this avalanche has a very low probability to occur in a certain lapse of time, you are not making the wise way to behave on such a problem. And obviously this is particularly important if the value of the receptors, so for example, a hotel, is high. So we have to work very much on this risk in order to avoid that we can have some damage due to a certain hazard of a certain severity that could produce effect on buildings and facilities. What about mitigation? This is the last topic of our lecture. Resilience is in some way a bottom-up process. So in some way we can try to be resilient, to adapt ourselves to the effect of climate, of global change. What about mitigation? Mitigation is more active, is more top-down, is more technical, sound process, trying in some way to obtain some effect on the, for example, scarcity of water resources due to climate change. Well, one way is to planning pumping rate in a sustainable way. So avoiding to overcoming the annual average recharge or to impairing environmental flows or to determine an intense drawdown. The drawdown is the lowering of piezometric level below a certain threshold, capable to increase the costs of groundwater pumping beyond an unacceptable threshold, not to induce salinization or subsidence effect, and not to impair the existing rights of groundwater exploitation. We have to take into account all these aspects if we want to pump in a sustainable way. It's not easy, but this needs the knowledge of the system, the knowledge of the groundwater budget, and the capacity to plan the water management in the proper way. It's important, for example, the concept of minimum vital stream flow, that is a flow that must be guaranteed to surface water system in order to maintain their survival and the conservation of ecosystems. We have to design all our activities of managing groundwater resources and groundwater exploitation in order not to overcome this minimal vital stream flow. I'm sorry because I see now a question in the chat. Isn't exploitation of groundwater in contradiction with the very definition of sustain? That's right, Siavash. It's a very logical comment that you have provided. I go back to the slide of the mitigation and the resilience of before. I'm sorry. I think it's important to go back to my provocation. Obviously, it was a provocation on the effect of fossil aquifer. Yes, if we pump in the Libyan desert in such a way, obviously we are pumping groundwater at a rate that is dramatically higher than the recharge. For that reason, in this location, we practically we shouldn't pump any water, because at the moment, the rate of recharge is much low. And so if we want to pump in a sustainable way, we shouldn't pump at this rate. I agree with you, but be careful. This is not the recharge of nowadays. We have to talk about the recharge of thousands of years ago. And for that reason, for that recharge, we are in a sustainable way. It's a provocation. Obviously, it's impossible to exploit the groundwater resources in this way. But be careful. It's useful for certain time of our society in order to cope with the effects of climate change, because groundwater is more resilient to the modification of the surface. And for certain time of the year, it could be useful for 10 years, for example, 15 years, to base our exploitation in order to overcome the effect of surface water droughts, for example. It's not a recommendation for forever, but to overcome the effects of surface water droughts. Because if we have surface water droughts, we have to overcome this problem in some way. And one of the ways is to base our exploitation on groundwater resources that are more resilient to the effect of climate change. I understand very well your comment, but I'm trying to explain that in such a way we can overcome in a transient way the effect of climate change. Well, let's go ahead. Obviously, yes, we have to avoid this phenomenon, the groundwater mining. The groundwater mining is the not sustainable exploitation. We cannot continue to groundwater pumping in a very intense way, higher the recharge rate. I know very well, but for some period of time and in some situations, groundwater is a very important way to overcome the drought's effect on surface water. Another provocation. I'm going to show you the three main springs in Emilia-Romagna. This is the Poiano spring. We are in the Secchia River watershed. This is perhaps the most important natural spring in Emilia-Romagna region, with the average discharge in low flow season around 200, 300 liters per second. Recall to this number, 200, 300 liters per second. This is the Nadia spring, is in the Zocca municipality in the Modena Apennines. It's a spring with the discharge during summer around 80, 90 liters per second. So a big lower respect to Poiano, but it's a very important spring. This is the Gabellina spring in the Secchia River watershed, Reggio Emilia Apennines, with a discharge around 70, 80 liters per second during summer. These three ones are the most important springs, perhaps, in Emilia-Romagna, between 200 liters per second and 80 liters per second. Well, let's observe these slides. And at a certain point, you will see something moving in the picture. This is a high-speed train that are running between Bologna and Florence along the main tunnels that are connecting Bologna and Florence through the Northern Apennines. Well, these tunnels were drilled, were excavated between 1996 to 2005, and they actually are draining groundwater. And you can see here on these two slides the discharge of groundwater coming out from these tunnels and going to the surface water networks. Well, this is a graph showing you the discharge of this system for different tunnels between Bologna and Florence. I would like to invite you to consider this graph in blue that is related to the Firenzuola tunnel. Firenzuola tunnel is one of the longest tunnels of this system that is crossing the main Apenninic divide between the Arno watershed to the south and the Santerno watershed to the north. Well, you see that this tunnel is providing groundwater drainage that during the summer season is about 300 liters per second. So make a comparison between this value, 300 liters per second, and the value of the discharge of Poiano Spring, that is about 200 liters per second. That is the maximum discharge spring up to now in Northern Apennines, natural spring. So up to now, at the moment, the maximum discharge groundwater drainage in Apennines is no more Poiano, but is represented by the Firenzuola tunnel of the high-speed train connection between Bologna and Florence. Why, with this slide, I'm making you a provocation, another provocation? Because if with the tunnel we cross the formation in Northern Apennines, we can obtain a high discharge. And this high discharge could represent a water resource for the period of droughts in the surface water system. At the moment, this discharge is not lost, but is discharged in the river system. But it's like a big spring. And this big spring could represent a way to cope with surface water droughts at the surface. Well, go ahead. Another smart solution to manage effects of climate change: the integrated management of surface water and groundwater. What is the integrated management? To try to understand that we cannot imagine surface water and groundwater like two isolated bodies, but they are strongly interconnected. 2,000 years ago, ancient Nabatei in the desert of Negev dig canals along ground contours in order to collect overland flow, and they convey surface water to underground tank to use this surface water for the dry periods. Also, in some situation, this is called rain harvesting, to collect the rainwater when there is much more water for rainfall, and to convey this excess of rainwater into the ground. This is an example of artificial recharge of aquifer, because if we have excess of surface water in certain period, we can use this excess of surface water to recharge groundwater. This is called artificial recharge. And this is a smart way to use surface water in excess to provide supply to groundwater. This is a way to contrast the loss of groundwater storage, to preventing or slowing saltwater intrusion, and to transfer the seasonal excess of surface water down to stressed groundwater reservoirs. We have a definition for this technology process. The definition is MAR, Managed Aquifer Recharge. And this is a planned human activity devoted to increase the groundwater sustainable yield through enhancement, so improvement of natural direct recharge, forcing infiltration of surface water into the aquifer. It's not an easy way, but in many situations, it's a good way to manage in a smart way an integrated approach of surface water and groundwater. You see some example. You can, for example, divert the discharge from a river, and you can convey the excess of surface water for example, through a recharge trench or a surface spreading basin, let this excess water to infiltrate into the ground and so to supply groundwater resources. Or you can also divert the surface water into wells and to inject directly the excess of surface water in deep groundwater. In some instances, this could be a very smart way to manage in an integrated way the excess of surface water down to recharge to groundwater. And this is a very important also way to prevent salinization of coastal aquifers. You see here, for example, you have the sea on the left, and obviously if you pump groundwater near the seashore, you induce a salinization of the aquifer. But on the other hand, if you inject groundwater in the aquifer, you can have the possibility to avoid salinization and to prevent the salt encroachment, to prevent the salt intrusion of the salty water from the sea to the aquifer. Or this is another approach. If you make groundwater pumping, groundwater abstraction near a river, with the pumping, you induce the lateral recharge from the river to the aquifer, and so you increase the recharge. And so in such a way, you have a high intensity groundwater pumping in the aquifer, but at the same time, you increase the lateral recharge from the river. And this is another smart approach to, in some way, consider groundwater as a part of the bigger hydrologic cycle. What about mitigation for the landslide? Here is more easy because to prevent landslide along with the correct planning, like the example of before, to properly plan the location of buildings, houses, hotels, urbanization, far from zones subjected to the risk of landslide. You have also to avoid excavation at the toe of a landslide, because if you excavate a slope at the toe, you can increase the destabilizing forces respect to the resistant forces, and you have the formation of a landslide and the destruction of buildings. Or avoid to overloading at the top of the slope, because to put a lot of load to the top of a slope can increase the destabilizing forces and so induce the formation of a landslide. And avoiding the water excess, because we know that rainfall increase the risk of landslide. But if we prevent infiltration in the landslide body, or we prevent rising of water table in the landslide body, or we prevent leakage, for example, of sewers, for example, of pipes, for example, in networks of pipes below the ground, we prevent the formation of landslide. So from the point of mitigation for the landslides, a correct urban planning and the proper activity to avoid overload or water excess are good mitigation activity to prevent landslide risk. I have uploaded in the Virtuale platform also some videos of the video that I have shown to you before. And I invite all to you, if you have time, to go with this link to a video produced by the International Association of Hydrogeologists for the 42nd International Conference in Rome in September 2015. This is a very short video, about 10 minutes, showing you the most spectacular springs and groundwater evidence in Italy, and so giving you an idea of the distribution of groundwater spring in the national territory. So I think it's a useful way to have you an idea of the importance of groundwater outcomes in our country, in Italy. Well, I am going to the end of my lecture, and obviously, if you have some question, I'm available here to reply to your question. Otherwise, Alberto, I'm finished.
Yeah, that's great. And thank you also for being on time. I hope that students may have questions.
I'm listening you a very low volume of
really? Okay.
Yeah, perhaps. No. Okay. Now I'm listening very well.
Okay, no, very good.
Yeah.
I see that, yeah, there was a question in the chat that you already addressed.
Yes.
So students, if you have any question, please. And I take this opportunity for reminding the interpreter, as soon as the video is ready, if you could please send to me a link for downloading it so I can put it on YouTube. Thank you very much. So I don't see any question. Students, you are many, more than 30, so I can't believe you don't have any question. Don't be shy. Professor Gargini can be challenged. He likes it. Okay, I don't see any question. So I will make a final call. I take this opportunity to remind the students, as I already said at the beginning, that the next lecture is on May 3rd. And I will also provide on May 3rd the logistic information, dates, and modes for the exam. And I also, as I said at the beginning, we are also planning to give you the opportunity to take a test exam in May. Of course, it will be just a test, so no registration of the mark, but just to practice on the quiz and the kind of questions that we may have. So final call. Any questions? Any question for Professor Gargini? Very good. So Alessandro, thank you very much. Thank you, students. And again, students, if you have any late question and any general question, you can use the chat on Teams, and we are periodically monitoring. Alessandro, grazie, thank you. And you see that the students are congratulating you on the chat. And grazie, and see you very soon. Maybe Alessandro, tomorrow, again, virtually, we will meet.
Okay. Thank you, Alberto. Bye-bye.
Okay. Bye-bye.
Bye-bye to all. Bye-bye to all.